This presentation is based on heartbeat classification using ECG signals. ECG signal represents the electrical activity of the heart. It consists of several waveforms called P, QRS, and T. The duration and shape of each waveform and distances between different peaks are used to diagnose heart diseases. An accurate diagnosis requires a thorough ECG analysis by an expert medical doctor, which is time-consuming. The development of an automatic ECG monitor can significantly improve the efficiency of the evaluation and diagnosis. The detection of cardiac arrhythmia using ECG signal consists of ECG acquisition, pre-processing, peak detection, feature extraction, and classification. Electrical signals are produced by contraction in heart walls, which drive electric currents and create different potentials throughout the body. By placing electrodes on the skin, one can detect and record this electrical activity. In practical scenario, different electrodes are placed on different parts of patient's body. These electrodes gives the view of electrical activities from different places of the body and thus gives different signals for a single subject. The physician determines the heart condition by combining a knowledge base from these different views of electrical activity of heart. ECG signals are accompanied by high-frequency noise and different artifacts. These artifacts creates the major hurdle in detection process. So, there is a need to remove these artifacts before detection using different filters. In our case, 2 artifacts accompanying the ECG signal are removed one by one. For this purpose, discrete wavelet transform is exploited to decompose the signal into approximate and detail components. The approximations are the high scale and yield low frequency components of the ECG signal, while the details are the low scales and yield high frequency components of the ECG signal. Therefore, by retaining the desired coefficients and discarding the other, noise-free ECG signal is obtained, which is ready for peak detection. Different ECG peaks plays a very important role in cardiac arrhythmia diagnosis. Accurate detection of these peaks helps in automatic heartbeat classification. The more accurate the detection, the more accurate will be the diagnosis. P and T peaks are detected using the fusion algorithm based on 2 event-related moving averages and fractional Fourier transform. To enhance our peaks, FRFT is applied to the noise and baseline drift-free ECG signal, which rotates it in the time-frequency plane. After enhancement, 2 event and cycle-based moving averages are calculated, which help in the generation of block of interests. These blocks are distinguished from the desired blocks by applying different thresholds. In each block, the maximum value in the corresponding enhanced signal is referred as a peak. For the detection of P and T peaks, our peaks are set to 0. Similar to the previous case, 2 moving averages depending on the P wave duration are generated. These moving averages help in the generation of rectangular pulses. Finally, a threshold based on the PR, RR and RT interval is applied to distinguish the generated blocks from the blocks that contain P and T peaks. If the detected peak lies within 30 milliseconds of the actual peak, it is referred as true peak. In this way, different peaks are detected. The estimation of different peaks can be used to find different time intervals of the ECG signal. Since these time intervals represent different cardiac conditions, they can be considered as features. Different features such as age, sex, PR and RT interval are extracted from ECG signal for classification. Machine learning is a type of artificial intelligence that allows software applications to become more accurate at predicting outcomes without being explicitly programmed to do so. Machine learning algorithms use historical data as input to predict new output values. Machine learning has different types of classification algorithms. We have used support vector machines and multi-layer perceptron for heartbeat classification. SVM is a supervised machine learning algorithm which can be used for classification or regression problems. It uses a technique called the kernel trick to transform the data, and then based on these transformations it finds an optimal boundary between the possible outputs. A multi-layer perceptron is a class of feed-forward artificial neural network. An MLP consists of at least 3 layers of nodes, an input layer, a hidden layer and an output layer. Except for the input nodes, each node is a neuron that uses a nonlinear activation function. MLP utilizes a supervised learning technique called backpropagation for training. It can distinguish data that is not linearly separable. The following part will show the results of our proposed algorithm. Classification algorithm is applied on MITB database. 70% of the feature data is allocated for training the model while 30% is allocated for testing purpose. Extracted features are passed to SVM and MLP classifiers. To compare the performance of our proposed classifiers, different performance matrices such as precision, recall and F1 score are used. Table shows the performance comparison of SVM and MLP classifiers on MITB-IH database. These classifiers classifies the heartbeats as normal, left bundle branch block, right bundle branch block, pace, premature ventricular contraction, and atrial premature contraction. MLP has better performance than SVM. We have also done the cross-database classification. MLP classifier is trained using the MITB arrhythmia database and tested on St. Petersburg INCART and SPH databases to classify normal, right bundle branch block, and premature ventricular contraction heartbeats. All three databases have different sampling rate. Therefore, all signals are resampled to 128 Hz. Different features such as age, sex, PR, and RT intervals are extracted. The overall accuracy of the trained model on INCART database is 99.85% while on SPH database is 68%. The detailed performance of the classifier for various CVDs in terms of precision, recall, and F1 score is shown in table. The proposed algorithm can be used in the futuristic cardiologist and the probe-less system. In such a system, probe-less ECG sensors will be placed on the patient body that will transmit signals with the help of Bluetooth to the processing device such as mobile. The received signal can be processed and passed to a machine learning algorithm for the automatic CVD diagnosis. The following part will show some practical work that has been done till now. The components used are AD8232 ECG sensor, the microcontroller Arduino Uno and the Bluetooth module HC05. AD8232 is a single-lead ECG sensor. It has 3 leads. One lead is placed on the left arm, one on the right arm and one the right leg. HC05 is the Bluetooth module, which sends real-time values to the connected mobile phone. Arduino Uno is the microcontroller which controls all the devices. Here is our ECG sensor and a mobile app which is currently doing real-time ECG monitoring. When a start button is pressed, app display all the devices paired with mobile phone. HC05 is a Bluetooth module that we are using for communication. When we select it from the list, it gets connected to our device. When the on button is pressed, the app starts displaying real-time ECG of the person. This app can plot ECG of the person up to 2000 points which can be increased and decreased according to the requirement. After plotting 2000 points, it will stop and after stopping, the previous data remains in the app and we can check the previous record by scrolling manually through the app. The raw data shown can be processed in the mobile app using the mentioned algorithms in this presentation to diagnose cardiovascular diseases.